In this session, we will going to discuss about CAN bus. CAN bus is an automotive vehicle network and it is used for communication between various issues in the vehicles. And it is widely used in all the vehicle designs today. This is the outline of this session. Initially, I will give an introduction to CAN bus. Then I'll explain about bus arbitration technique in the CAN bus. We know that each node in the CAN bus can transmit the data. If two or more trying to transmit the data at the same time, then we need to select one node for the transmission, and this is done by the bus arbitration techniques. After bus arbitration techniques, we will move on to CAN frame format, and here we will discuss about the various fields in the CAN frame. There are a lot of sensors and actuators is present in a modern vehicle, and these sensors can be temperature sensor, accelerometer, velocity meter, fuel gauge, etc. And the actuator can be side mirror motor, headlight, or it can be a windscreen wiper, etc. And each sensors and actuators are controlled by some electronics unit, and it is called electronic control unit or ECUs. And for the proper operation of the vehicle, it is needed that there should be a continuous reliable communication between these devices. And if we use separate cable, separate copper cable for communication between these devices, we may needed maybe thousands of copper cables. So in order to reduce the number of the copper cable needed for the communication, Robert Bosch invented the CAN bus, and it is released in 1986. CAN bus uses a message-based protocol. There can be lot of nodes attached to a CAN bus, and each node is capable of sending and receiving the messages. If one node transmits a message, all other nodes in the CAN bus can receive it, and depending on the message content, each node will either process or ignore the message. And CAN bus uses a multi-master architecture. It means that all the nodes in the CAN bus can transmit the message at any time. And if some two or more nodes trying to transmit the message at the same time, there will be some collision will happen. And in order to overcome this collision, the CAN bus uses a priority based bus arbitration technique. Here in order to indicate the priority, a unique identifier is used, and this unique identifier determines the priority of the message, and depending on the priority of the message, the bus arbitration technique will only allow one message to be transmitted. The CAN standards contain two versions, version 2.0a and version 2.0b. Version 2.0a is the standard version of the CAN, and it uses an 11-bit identifier. With the help of this 11-bit identifier, we can specify 2 raised to 11 or 2048 priority based message identifiers. And for most application it is enough, but some cases we may need more message priority based message identifiers. In order to obtain that, we will use version 2.0b of the CAN standard, and it is called the extended CAN. And this extended CAN uses 29-bit for the identifier specification, and with the help of this 29-bit we can specify up to 2 raised to 29 or half a billion message identifier. And this version 2.0b also support 11-bit identifiers also. The controller area network or the CAN bus is widely used for lot of applications. The major area of the CAN bus application is the automotive industry. In the automotive industry, it uses for in passenger vehicles, trucks, buses, cars, etc. And it also uses in agricultural equipment, electronic equipment for aviation and navigation, industrial automation and mechanical controls, elevators, escalators, etc. and for building automation and for medical instruments and equipments. A modern automobile has as much as 17 ECUs or electronics control unit. These ECUs are used for managing various sensors and actuators in the automobile. And for the proper operation of the automobile, there should be a good communication between these ECUs. Here we will use a CAN bus for the communication between the ECUs. And the bus line of the CAN bus contain is made by two twisted pair copper cables, and the one cable is labeled. Here we can see that the one cable is labeled as CAN H and the other is labeled as CAN L. CAN H is the high voltage line and CAN L is the low voltage line, and various nodes in the CAN bus can be attached to the bus line parallelly, and each node in the CAN bus contain a CAN transceiver, CAN controller and a microcontroller. The CAN transceiver is taking care of transmission and reception of the reception through the CAN bus, and the CAN controller will manage the CAN transceiver, and the microcontroller will used for the logic. Depending on the CAN controller, the CAN can be classified into two types: basic CAN and full CAN. Basic CAN is the cheaper version of the CAN, and in the basic CAN, the CAN controller contain only receive buffer and transmit buffer, and this receive buffer is arranged in a FIFO, and if the FIFO is become full, the newly arrived message will drop. So it is better to empty out the FIFO by the microcontroller when it is possible. And this FIFO is also give an option to filter out the messages using the identifier. Full CAN is the more functional version of the CAN, and the CAN controller buffer in the full CAN is called mailbox. And when the CAN controller receive a message, it will check the mailboxes to see whether the host controller subscribed the message, and if so, the CAN controller will save the message and notify the host controller, else the message will be discarded. CAN bus offers lot of features and benefit over other types of communication standards, and these are the benefits of CAN bus. Firstly, it is a multi-master architecture. It has a multi-master architecture. It means that each node in the CAN bus can transmit the data at any time. And next feature is that it support automatic prioritization of message and automatic arbitration. And this is done by a message identifier field which is present in the CAN frame. And it also offers high reliability over other types of communication standards. And this reliability is achieved by using various error checking and detection scheme in the CAN frame. And it also a robust standard because it can operate in very difficult electrical environments. And it also allow a flexibility for the configuration of the CAN nodes. Since CAN bus line is made by simple twisted pair lines, and this CAN node is arranged in parallelly, we can add and remove newer nodes very easily. And the CAN bus line can be very long. Sometimes it can be up to 1 kilometer long. And since the CAN bus is made by twisted pair copper cables, it is very low cost. Along with the advantages, CAN has fewer drawback also. The main drawback of the CAN is it support maximum data rate of 1 Mbps only, and a CAN frame can carry only 8 bytes of data at a time, and there is a lot of protocol overhead for carrying or for sending a data frame. A CPU, a CAN controller and a transceiver together form a CAN node, and various sensors and actuators are connected to the CPU. And this CAN controller will store the message which is received from the CAN bus, and also store the message which is sent to the CAN bus. And this transceiver do the communication task. It contain a CAN transmitter and a CAN receiver. Depending on the speed, flexibility and payload capability, can be classified into 4 types. First one is high speed CAN. Second one is CAN with a flexible data rate. And third one is low speed or fault tolerant CAN. And last one is single wire CAN. In the high speed CAN, the data rate can be achieved up to 1 Mbps. But in the case of flexible data rate CAN, the data rate also can be achieved up to 1 Mbps speed, and it also support a CAN payload with 64 byte in a single message frame. And in the case of low speed CAN or fault tolerant CAN, the data rate can be reached only up to 125 kilobit per second, but it has some fault tolerant capabilities. And lastly, for the single wire CAN, the data rate can be only achieved up to 33.3 kilobit per second. But for the establishment of single wire CAN, it only need a single wire for communication. A twisted pair cable of impedance 120 ohm is normally used for communication, and this cable can be shielded or unshielded. In the previous slide, I gave an introduction to bus arbitration. CAN has a multi-master architecture. It means that the devices connected to the CAN bus can transmit the data at any time. If two or more devices started to transmit the data to the bus, then there may be some collision will occur. And the bus arbitration technique is used to prevent the collision or prevent such thing from happening. And there are two methods for bus arbitration. The first method of bus arbitration is centralized method. Here a single bus arbitrator performs the bus arbitration. And the second method of bus arbitration is the distributed method. Here all the nodes in the system take part in the bus arbitration. In the case of CAN bus, the distributed approach of bus arbitration is using, and the CAN bus achieve this bus arbitration with the help of dominant and recessive bits. In order to understand the dominant and recessive mode of the CAN bus, we can consider this diagram. Here we can see that there are three transceiver blocks of the CAN nodes. There are three CAN nodes and these are the transceiver nodes. And each transceiver node is connected to a bus line. And this bus line is connected to plus 5 volt through a pull-up resistor. And in this case, we can say that the dominant mode of this bus line is 0 volt. Because if any of the transistor is turned on, then the bus line will be connected to the ground potential. Here 0. So the bus line voltage will be 0. And in order to make the bus line to a plus 5 volt, all the transistors should be turned off. So we can say that the resistive mode of this bus line is plus 5 volt. And the same thing can be seen in this state diagram. Here S1, S2, S3 are given as the input to the transceiver block. And if any of the input is 0, then output should be 0. In other words, if any of the input is dominant level, then output should be shows dominant level. Bus level should be shows dominant level. And if in order to set the recessive level in the bus line, we have to set all the nodes to a recessive level. Then only the bus level should be equal to the recessive level. Here recessive level is plus a logic 1 or plus 5 volt. Now we can go through the CAN bus arbitration procedure. And this is the timing diagram of the various devices which is connected to the CAN bus. And these are the arbitration ID of the various nodes which is connected to the CAN bus. And this is the arbitration ID of the node 1, and this is the arbitration ID of the node 2, and this is the arbitration ID of the node 3. And this is the frame format of the CAN bus frame. And in order to understand the CAN bus arbitration, first we have to get a clear idea about the dominant mode and recessive mode. And previously I give an introduction to dominant mode and recessive mode. And here in this particular case, the dominant mode is bit 0 or high voltage, and recessive mode is bit 1 or low voltage. Suppose two or more nodes in the CAN bus want to transmit some data, and if they are trying to transmit the data at the same time, then there will be some conflict will happen. And in the case of CAN bus, there is a automatic CAN bus arbitration procedure, and this procedure, which is followed by all three nodes, will help to resolve this conflict and also prioritize the transmission, and this is called automatic CAN bus arbitration. Now we will see what is automatic CAN bus arbitration procedure with the help of this timing diagram. Here there is node 1, node 2 and node 3. All three nodes want to send some data. So initially the node 1, node 2 and node 3 will check whether any data transmission is going on the bus. So the node, this node 3 node will check the voltage level in the bus and verify that there is no data transmission is going on. So these nodes will start the data transmission by sending a start of frame bit. After sending the start of frame bit, they will try to start to send the arbitration ID. The arbitration ID of each node is unique, and this arbitration ID is based on the priority of the messages. And here we can see that the start bit of the arbitration ID of the node 1, node 2 and node 3 all are 0. So each node will place the arbitration ID in their bus, in the bus. Here so the node 1 will send the arbitration ID, set the arbitration ID 0, and node 2 set the arbitration ID 0, and node 3 will set the arbitration ID 0. And bus also, since both nodes are sending the same arbitration bit, the bus also shows the same bit. And these nodes will verify whether their send and the send arbitration ID is same as that of the bus arbitration ID seen in the bus. Since everything is same, they will continue to send the second bit of the arbitration ID. But in the case of node 2, the second bit of the arbitration ID is 1. Here we can see that the second bit of the arbitration ID is 1 in the case of node 2. But in the case of node 1 and node 3, the second bit of the arbitration ID is 0. And here, in this particular case, the dominant mode is the 0 or 0 bit. So there in the second clock cycle, node 1, node 2 and node 3 are sending the second bit of their arbitration ID. So node 1 will send the arbitration ID is 0, and node 2 will send the arbitration ID 1, and node 3 will send the arbitration ID 0. And since the dominant mode is 0, the bus will set the dominant voltage to 0 voltage. And here in this case, node 2 will identify that it is placed a 1 bit, but it is seen a 0 bit in the bus line. So node 2 will understand that there is some other node which has higher priority than his is trying to send some data. So node 2 will back off and go to the listen state. And so from this time onwards, only node 1 and node 3 is trying to send the data. And at the third clock cycle, so node 1 and node 3 will send the third bit of their arbitration ID. Here the arbitration ID, third bit of the arbitration ID of the node 1 and node 3 is 0. So node 1 will place 0 and node 3 will place the 0 in the bus line. So the bus line also shows 0. So node 1 and node 3 will continue with the transmission. But at the fourth bit of the arbitration ID of the node 1 is 1, and the arbitration ID of the node 3 is 0. So at the fourth clock cycle, node 1 will place the fourth bit of arbitration ID 1, and node 3 will place the fourth bit of arbitration ID 0. And but here in this case, the dominant voltage level is 0. So we can see that only the 0 voltage will be appear in the bus line. So node 1 will understand that it is placed a 1 bit, but a 0 bit is appeared in the bus line. So it understands that some other node with higher priority is also sending the data at the same time. So it is backoffed. So node 3 will continue with the transmission. So with the help of this dominant and recessive bits, the CAN bus achieves an automatic arbitration. And in the CAN bus standard 2.0a, the arbitration ID is 11 bit long. But sometimes this is not sufficient. So the CAN bus standard 2.0b uses a 29-bit arbitration ID field. So with this arbitration ID field, we can prioritize up to 500 million messages. Here we can see that basic format of a CAN frame. Each CAN frame is started with a start of frame field. The start of frame field is used to indicate the beginning of the frame. After start of frame field, it comes 11-bit arbitration ID. This arbitration ID is used for prioritizing the messages as well as automatic arbitration purpose. After this arbitration ID, there is one SRR and IDE fields. This IDE field is used for extending the arbitration ID, and this, if the IDE field or identification extension bit is set, then it is saying that the arbitration ID needed to be extended. Such cases, there is an next field is an 18-bit arbitration ID. After this extended arbitration ID, it comes RTR field, R0 field and DLC field. And this R0 field is used as a reserved bit, and it can be used for future protocol extension phases. And the DLC field contain the length of the is nothing but the data length code, and it indicates the length of the data. And followed by the DLC field, next field is byte data field. Here nothing but the actual data. Here we send the actual data. After the data field, then it comes CRC field. CRC is the short form of cyclic redundancy check, and it is used for detecting errors in the transmission by taking the CRC sum of the cyclic redundancy check sum of the packet. Followed by the CRC, it comes acknowledgement field, and depending on the values of the acknowledgement field, we can verify whether the data is received faithfully. And finally, the end of frame field, and it indicates the end of the data frame. CAN support 4 types of frames. The first one is data frame. This data frame is used to carry data. In a data frame, it is possible to carry up to 8 bytes of data, and it also contains a CRC field. This CRC field is used to detect the error happening in the data. And the second type of frame is remote frame, and this frame is used as a request to retransmission of certain data. And the third type of frame is error frame. When an error detected, this type of frame is transmitted. And the last type of frame is overload frame, and this overload frame is used to provide a delay between data and remote frame. CAN is a very reliable communication standard. This reliable means it can achieve zero error communication, and this is made possible by various error detection and correction methods which is used in the CAN standard. When a receiver receives some frame, it will check for frame integrity using frame check. Then it will check for bit stuffing errors. And if the frame integrity is found okay, then it will go look the CRC field, and this CRC field contain the checksum of the data. And if the checksum of the data is not matches the data received, then the receiver node will raise a NAC signal, not acknowledgement signal, and this signal will be detected by the transmitter, and the transmitter will resend the data. CAN bus is a synchronous standard. Since it is a synchronous standard, there should be one common clock which is maintained in both the transmitter and receiver. But in the case of CAN bus, there is no electrical line for communicating the clock. So the CAN bus is regenerating the clock from the received data. And for the proper operation of the clock regenerator circuit in the receiver, the data should have enough transition from low voltage to high voltage and high voltage to low voltage. In order to maintain enough transition from this low voltage to high voltage and high voltage to low voltage, we will use bit stuffing. In bit stuffing, if a consecutive 5 consecutive 1 bit or 5 consecutive 0 bit happen, then we will add an opposite polarity bit to the data, and this will give a transition in the encoded output voltage level. So the clock recovery circuit in the receiver will be able to regenerate the clock. If a CAN controller identifies there is an error happening in the CAN bus, the CAN controller will send the not acknowledgement signal to the transmitter, and so the transmitter will mark the frame as an erroneous frame. Thank you.